Welcome back. In this video, we're going to look at topics related to the convergence of the Fourier series and how this relates to signals with discontinuities like the square wave. Now, Fourier had it that any periodic signal could be represented by a Fourier series. Now, although this isn't quite true, as we'll see in a little bit, it turns out that the Fourier series can be used to represent an extremely large class of periodic signals, including periodic signals with discontinuities like the square wave, and all other periodic signals that are important in practice. So let's look at the question of when does a periodic signal x of t actually have a Fourier series representation. One class of periodic signals that can be represented through the Fourier series are signals that have finite energy over a single period. So signals that satisfy the integral over one period of magnitude of x of t squared dt is less than infinity. When this condition is satisfied, we're guaranteed that the coefficient Cn equals the integral from minus infinity to infinity of x of t e to the minus j n omega naught t dt, that these coefficients are finite. Also, if we let xn of t be the truncated Fourier series approximation by using the coefficient Cn in the complex exponential Fourier series expansion for absolute value of n is less than or equal to capital N, we can define little e sub n of t to be the approximation error, so x of t minus xn of t, the truncated Fourier series, and then we can define the energy in this approximation error to be capital E sub n of t equals the integral over one period of magnitude of little e sub n of t squared dt. And it turns out that if x of t has finite energy in one period, which means it satisfies this condition, then we're guaranteed that the energy E sub n in the approximation error converges to zero as n goes to infinity. So there's no energy in the approximation error when n goes to infinity. Now note that just because the energy in the approximation error goes to zero as capital N, the number of terms, goes to infinity, this does not imply that the signal x of t and then its Fourier series representation are equal at every value of t. What this does say, however, is that there's no energy in their difference. And we'll see this very evidently towards the end of this video when we look at the convergence of the finite Fourier series approximation x of n of t for the square wave that we saw in the example at the end of the previous video. Now, an alternative set of conditions developed by Dirichlet guarantees that x of t equals its Fourier series representation except at isolated values of t for which x of t is discontinuous. And at these values, the infinite series converges to the average of the values on either side of the discontinuity. There's three conditions that constitute the Dirichlet conditions. The first condition is that over any period, x of t must be absolutely integrable. So the integral over one period of magnitude of x of t dt has to be less than infinity. And this guarantees that each coefficient Cn will be finite, since Cn is less than or equal to 1 over t naught times the integral over one period of the magnitude of x of t e to the minus j n omega naught t dt, but this is simply 1 over t naught times the integral over one period of magnitude of x of t dt. So if this here, the integral over one period of magnitude of x dt is less than infinity, then we're guaranteed that these Fourier series coefficients Cn are finite. As an example, one periodic signal that violates this first Dirichlet condition is the signal defined by x of t equals 1 over t for 0 less than t less than or equal to 1, and is periodic with period 1. And if we look at a plot of this periodic signal x of t, we see that it does not satisfy this first Dirichlet condition since the integral over one period is infinity. The second Dirichlet condition is that in any finite interval of time, x of t is of bounded variation. Now, what does it mean x of t is of bounded variation? It means that there are no more than a finite number of maxima and minima during any single period of the signal. An example of a function that meets condition 1 but not condition 2 is the signal defined by x of t equals sine of 2 pi over t for 0 less than t less than or equal to 1 and is periodic with period 1. And if we plot this periodic function, its plot looks something like this. So this function, which is periodic with period 1, is absolutely integrable within each period because the integral from 0 to 1 of magnitude of x of t dt is less than 1, but it has an infinite number of maxima and minima in each period, which is why it does not satisfy the second Dirichlet condition. The third and final Dirichlet condition is that in any finite interval of time, that there's only a finite number of discontinuities, and each of these discontinuities is finite, or in other words, x of t is piecewise continuous. An example of a signal that violates this third Dirichlet condition is a signal that's periodic with period 8, but in each period, say for 0 less than or equal to t less than 8, the value of x of t decreases by a factor of 2 whenever the distance from t to 8 also decreases by a factor of 2. For x of t is 1 for 0 less than or equal to t less than 4, 1/2 for 4 less than or equal to t less than 6, 1/4 for 6 less than or equal to t less than 7, 1/8 for 7 less than or equal to t less than 7.5, and so on. And if we look at a plot of this periodic signal, we see that there's an infinite number of discontinuities in each period, which violates the third Dirichlet condition. Now, to gain some additional understanding of how the Fourier series converges for a periodic signal with discontinuities, let's revisit the example of the square wave at the end of the last video. I'm going to look at a plot of xn of t, the truncated Fourier series approximation of x of t, which is a symmetric square wave for different values of n. So here's n equals 1. As you can see, we only have the first harmonic. For n equals 3, we have all the way up to the third harmonic. Here's n equals 19, so we have all the way up to the 19th harmonic, n equals 39, and n equals 79. Now, since the square wave satisfies the Dirichlet conditions, the limit as the number of terms n goes to infinity of xn of t at the discontinuities should equal the average value of the discontinuity. And we see from these plots that for any n, xn of t has exactly that value at the discontinuities. If I look at n equals 1, the finite Fourier series approximation xn of t converges to the average value of 0 and 1, which is 1/2. N equals 3, same thing, xn of t equals 1/2 when the square wave goes from 0 to 1 and then back from 1 to 0. And even if I run, say, n equals 19, you can still see that the truncated Fourier series approximation xn of t converges to the average of the values on either side of the discontinuity, which in this case is 1/2 at the discontinuities. Also, for any other value of t, say t equals t1, that's not a discontinuity, we're guaranteed by the Dirichlet conditions that the limit as n goes to infinity of x sub n of t1 is equal to x of t1. And as we keep increasing the value of n in our plot of the finite Fourier series approximation of the square wave, at any time value that's not a discontinuity, the truncated Fourier series gets closer and closer to the actual value of x of t. For instance, here's n equals 20, here's n equals 60, here's n equals 100, here's n equals 200, and then when I run n equals 2000, pretty much the finite Fourier series approximation xn of t converges exactly to the actual value of the square wave at all time points except at the discontinuities. Now, the interesting effect is that the behavior of the partial sum around the discontinuity exhibits these ripples, and that the peak amplitude of these ripples doesn't decrease at all as we increase the value of n. It doesn't matter how large I increase n, the peak amplitude of the ripples pretty much stays the same. For instance, here's what the ripples look like when n equals 200, and I can increase n from 200 all the way to 2000, so by a factor of 10, and the height of the ripples stayed exactly the same. And Gibbs showed that these ripples were actually correct. And specifically for discontinuity from 0 to 1, the partial sum of the Fourier series has a maximum value of 1.09, so an overshoot of 9% of the height of the discontinuity. And it turns out that the closer T1 is to a discontinuity, the larger n must be taken in order to reduce the error below a certain point. And so as n increases, the ripples become compressed towards the discontinuity, but for any finite value of n, the peak amplitude of the ripples still remains constant. And this behavior is what's known as the Gibbs phenomenon.